Okay, this is Unit 9. This is the concept of thermochemistry. This is all about the amount of heat that is released or absorbed when chemical reactions take place. So, let's jump right into some terms. So, in chemistry, there's this weird term called enthalpy. The definition of enthalpy is the amount of potential heat energy used or released in a system at constant pressure. Now that's a pretty technical definition. Let's simplify this a little bit. When we say system, what we're really talking about is during a reaction. Okay, so it's the amount of heat energy that's taken in or lost when a chemical reaction takes place. Now, they add this little bit here about constant pressure. You don't have to worry about that because all of our reactions that we're going to carry out are taking place at constant pressure. That's there because later on, if you do more in chemistry and more in thermochemistry, that becomes important, but it won't be important for us. All right, so for all intents and purposes, that little bit doesn't really matter. Okay, so whenever chemical reactions occur, some bonds are broken and some new bonds are formed. Every chemical reaction that we have written out, both of these two things happen. So let's look at a very simple reaction here. All right, so let's say that I was to react hydrogen with iodine to form the compound hydrogen iodide. Now I'll balance it. And so that's a pretty straightforward reaction. If I asked you to, you know that you could classify this. What kind of reaction is that? It's a synthesis reaction, yeah. Okay, now if we look a little closer as to what's actually happening. Hydrogen is a diatomic molecule, which means you have two hydrogen atoms bonded to each other. Iodine also is diatomic. When we form the compound hydrogen iodide, we get a bond formed between hydrogen and iodide, but I'm going to draw this twice because two of those are formed. So, during the course of this reaction, these bonds right here in green are the ones that are being broken. The bond between the H's, the bond between the I's. Those have to be broken. And the bonds that are going to be formed are here in blue. So the act of breaking bonds uses energy. Think about that. That should make sense. You have a molecule and you want to separate the atoms. You're going to have to shake those two atoms hard enough where the bond is broken to break it apart. Whenever bonds form, energy is released. Forming bonds releases energy. So they're very opposite. Okay, so chemical reactions, energy or enthalpy. When we say enthalpy, we say energy. A lot of times we mean the same thing. It requires energy to break bonds. Energy is released when bonds formed. So let's look at a diagram here. Actually, I'm going to talk about these terms here first. Okay, so while we're defining terms, let's jump down here. Okay, so the definition of energy is the capacity to do work or cause heat transfer. There's two types of energy. The first is potential, and the key word with potential energy is that it's stored. Energy that's stored. So some chemicals store a lot of energy. Some don't have very much. It all kind of depends. Some are pretty obvious. Like if I said in gasoline, you should get the idea. You should know that there's stored energy in gasoline because if you burn it, it releases a lot of energy, right? There's a reason why you have it around so that you can, use it as a fuel. Kinetic energy is energy in action. Energy in action. Energy of movement, basically. So kinetic energy should be obvious. anything that is moving, it has kinetic energy, right? Now, talk a little bit about movement. With motion, obviously, if something moves from point A to point B, it's moving. Heat energy is the energy caused by the rapid release of energy. But vibration is not obvious. Let's talk a second about vibration. Let's say you have a solid. Remember that a solid, the particles are in a rigid lattice, and they're orderly arranged. Now, what you don't realize is that in every solid, the atoms are vibrating. They're kind of moving, swaying back and forth, right? Each one of them is moving to the left, moving to the right, moving up, moving down, in every possible angle, a little bit, sitting in place. It's all happening. Now, the actual solid itself doesn't go anywhere. It's still sitting wherever it's sitting, but all the atoms within it are moving. And that's the vibrational movement that we're talking about. So even in a solid that doesn't appear to be moving, there is movement. So maybe to make sense of this, imagine like a car hood, like sitting in the sun in a hot summer day. How come you get burned when you touch a hot piece of metal in the summer? It's because the atoms are moving so fast that much energy is transferred to you, which is why you burn yourself. But if it's a cold day, the atoms are not vibrating as much, and you don't get burned. But they're still vibrating, even if it's cold. So, does that make sense, guys? In any solid, atoms are still vibrating. Okay? Yeah, Tammy.
When something's moved, something's like this, like it burns you, so are they moving like really slow still?
So like a freezer burn? So if something's really, really cold, it's not that it burns you, but there's so much energy that's being taken from your skin when you touch it that your nerves are triggered and they're sending a message to your brain that something's wrong with what you're touching. So, but no, you're not getting burned, although it can damage your skin if it's too cold relative to the temperature of your skin. Yeah. Okay. All right, so two types of energy, potential, kinetic. All right. Law of conservation of energy. This term, we talked about this or similar law back in Unit 1 when we talked about the law of conservation of mass. How matter cannot be created nor destroyed. Well, the same idea, energy cannot be created nor destroyed, but it can be converted, right? You can change energy from one form to another. So, for example, you can change from potential to kinetic, but all of the energy that was there before is accounted for. So, if you've got red canister gasoline in your garage, you can measure the potential energy of burning, of combustion in that gasoline, and then you can actually ignite it and measure the temperature, because at that point it's kinetic energy. But whatever the amount was before must equal the total amount after. It's just changed, but it's still accounted for. Okay? All right. And so next we're going to talk about heat flow. So if chemical reactions release or absorb energy, and energy is not created nor destroyed, the energy must go somewhere. So basically, hot objects transfer energy in the form of heat to cold objects. Energy flows downhill. It always goes from the hotter to colder. always. So let me give you a scenario here. I'm going to add a page here just to clarify. Let's say that I have a cup of water, right? And let's say this cup of water is 80 degrees Celsius. Okay, let's say that the room temperature in here, let's say it's 20 degrees. If I take this hot cup of water and set it down on the counter, what's going to happen? Don't overthink it. Just have a hot cup of water sitting on the counter. What's going to happen? It's going to cool off. So what's going to happen is heat. It's going to give off heat, right? Because the cup, the water, is warmer than the room. So it's going to give off lots of heat at first. And let's say it gave off heat, and let's say it's now at 50 degrees. The room is still 20 degrees. What's going to happen now? The cup of water is 50 degrees. The room is 20 degrees. It's still giving off heat and then a lower temperature. Let's say it gets down to 25 degrees. At 25 degrees, it is still warmer than the room. The hotter object always gives heat to the colder object. Even if it's not a huge difference. 5 degrees is not a huge difference, but it still has more heat. It's going to give more energy. It's going to give it off. Now, eventually, we're going to get to room temperature. Now, what has more energy, the room or the cup? The temperatures are equal. So when this happens, any energy that's given off is also absorbed in the same amounts. Energy released equals energy absorbed. This is what we call thermal equilibrium. Now, in this room, as long as this room stays 20 degrees, the temperature of the water will stay the same temperature as the room. Unless the temperature of the room changes, that's just the temperature it's going to be at. Okay, let me give you another example. So let's say I have a cup of water. But let's say I get this one from a water cooler. Let's say it's 2 degrees Celsius. It's in the same room. What's going to happen? It's going to get warmer. Now it goes up to 10 degrees. What's going to happen? 10-degree water, 20-degree room, what's going to happen? Still going to get warmer. Eventually, you will get to the same temperature as the room. And that's thermal equilibrium again. So it doesn't matter if something's hotter or colder, things will get to the same temperature because the hotter object always gives energy to the colder object. Okay. Did we skip? Yeah, let's go back to these diagrams up here. All right, so let's say I have a reaction taking place in a flask. So the reaction's taking place here inside the solution. And this reaction is going to give off heat. That's why the arrows are pointing away from the flask. If a reaction gives off heat, that's what we call an exothermic reaction. The exo is a Latin prefix. It means to exit or to leave. So that means heat is leaving the reaction.
You don't have that.
Oh, are you missing the slide?
Yeah.
Okay. It's don't worry about it. Write down the term exothermic, right? So exothermic, heat leaves the reaction.
Can you call it if it's not like that?
Okay, then don't worry about it. It's okay. This picture may have been added later, last minute. In another reaction in the flask, if we have a reaction and all the heat arrows are pointing towards the flask, that means the reaction is absorbing heat. If the reaction absorbs heat and you touch the flask feels cold. Whereas here, this one feels warm. We've had several reactions where I've asked you to touch the test tube after the reaction and tell me if it's going to get warmer or colder. Okay. That's one way we can tell what type of reaction it is. In an endothermic reaction, the term endo is Latin, right? It means within or inside. Kind of like in biology, the difference between an endothermic or an endoskeleton and an exoskeleton. If something's endothermic, it's taking heat in, it is absorbing heat, and when you touch it, it's absorbing heat from your finger, it makes it feel cold. Okay. So if we were to look at a graph, this graph shows us the potential energy of the reactants versus the products. So in this reaction, the potential energy of my reactants starts out here, right, whatever value that is. During the course of the reaction, the product's potential energy is lower. So that means during the course of this reaction, when we calculate the change in H, which remember H stands for enthalpy, the symbol H, which for all practical purposes, enthalpy equals energy, okay? So the change is H final minus H initial. So H final is down here, H initial is up here. So just to put some numbers on it, let's say this was 90 and let's say this was 10. For this reaction, a delta H would be 10 minus 90, or in other words, negative 80 kilojoules. The fact that it's negative tells you that energy was released. So you should recognize if there is a negative sign, that is telling you the reaction is exothermic. That's important. That's very important. Highlight it, circle it, whatever you need to do. Negative sign means exothermic. Okay, so in an exothermic reaction, if there was a loss of energy, that means more energy was released when the bonds formed than you needed to break the bonds. Right? Because breaking bonds requires energy. Released is losing. So if the overall is negative, that means we must have released more. Than absorbed. Okay, we'll come back to that later. If that's a little confusing, we'll go over some more examples of that. Let's look at a different graph. Endothermic reactions. So here we're looking at potential energy, the enthalpy on the y-axis again. And just to put numbers here, let's say this was 70, let's say this was 20. Delta H would be H final minus H initial. So H final is 70, H initial was 20, so the delta H is positive 50. So endothermic is when you have positive values of delta H. That is just as important. Okay? Positive value for delta H, that's an endothermic reaction. Heat was absorbed. And again, the tricky part about these reactions is because the reaction here is absorbing heat. The beaker is losing heat, so the beaker feels cold. Because all of the heat that was in the glass, all of the heat that was in the water is being absorbed by the reaction. When I say reaction, I mean the reactants and products. Okay, so energy used to break the bonds was more than the energy released, which is why the overall value is positive, because more energy absorbed than released. Okay, I know I'm throwing a lot of terms at you guys, but we need to kind of get these out of the way so that we can do some constructive problem solving. All right, we already covered these terms. So one more set of terms, and then you'll actually kind of see how this pulls together. So the term heat. Heat is the transfer of energy, so we've been talking about this. It's the transfer of energy from one substance to another. It has a symbol. We use the symbol Q because we'll be plugging it into mathematical formulas, so it has to have a symbol. So we use Q for it. Calorimetry, I alluded to this earlier. It's the measure of science of measuring heat. Now, if you look at the first part of the word, calorie, you know calories in the context of food, and you know that foods with high calories, have more energy, and therefore, when you count your calories, how much food you need to eat per day, all that is labeled on food products. So we can actually convert calories into joules. A calorie is equal to 4.18 joules. So we'll use that as conversion to go back and forth. Okay, temperature. Temperature is a measure of the average kinetic energy of a substance, right? If you have a sample of anything, a sample of water, a sample of a gas, you take the temperature, it's the average kinetic energy, right? When something absorbs heat, the temperature goes up. If something releases heat, the temperature goes down. Okay, here with these two terms is where it gets kind of weird. So this term heat capacity, it's defined as the amount of energy required to raise the temperature of a substance by 1 degree. Now, let me explain here with maybe a little diagram. I've got, again, a cup of water. We're going to be using cups of water a lot in this unit. So I've got this cup of water here. Let's say it's 100 grams of water. Is it conceivable that I can take this cup of water, put it in the microwave, and increase the temperature? Let's say right now it's 20 degrees. Can I get this water to, say, 60 degrees when I'm making hot chocolate by putting it in a microwave? Sure I can. That's no problem, right? I just put it in for, a minute, take it out, and it's changed from 20 to 60 degrees. The temperature has gone up. Okay, so if I was able to do that with that cup of water, and that was 100 grams, let's say we have a different scenario. Let's say you're on an ocean island. And so all of this water here in the ocean. Let's say you're in the Bahamas. Let's say the temperature is also 20 degrees. Can you get that water in the Bahamas, in the ocean, up to 60 degrees?
Yeah.
Really? How?
Use the sun.
Use the sun. What are you going to turn the sun on? What? How?
Yeah.
Okay. So, what's the fundamental difference between the cup of water and the ocean?
It's bigger.
Yes. Okay. More mass. So, as far as going back to the term heat capacity is the amount of energy required to raise the temperature by 1 degree. Which one of these, let's just change the temperature even from 60. Let's just say 21 degrees. 21 degrees. Which one of these is going to take more energy to increase the temperature by 1 degree? The ocean, right? So, more mass means higher heat capacity. Means there's more energy needed to do that. Okay. So, heat capacity depends on mass. It's a direct relationship. More mass, the greater the heat capacity. So then there's this term, specific heat capacity, which if you look at the definition, it looks a lot like the heat capacity definition. It says the amount of energy required to raise the temperature by 1 gram by 1 degree. The difference between these two terms is that this is heat capacity per gram. And that actually makes it more useful, because now it doesn't matter what the mass is anymore. It's on a per gram basis, right? So it's the symbol for heat capacity is C. The units are joules per degree Celsius, just like heat capacity was joules per degree Celsius. But the difference is we're dividing it also by grams. To give you an analogy, remember density? Could you identify a metal by its density? Remember our lab from Unit 1? You had lead, you had aluminum, and you measured its volume, you measured its mass, you calculated the different densities. Yeah, you could identify different metals by their density. But if I only told you the mass, you would not be able to identify the metal. So one number is useless, one number is useful. Here, the heat capacity is not that useful. Specific heat capacity is more useful, and that's why we're going to be using this most of the time. All right. So that's a lot of terms. Why did we go over all of those terms? It's so that we can be able to calculate. We can start our calculations with heat. The first equation you're going to learn here is called the heat flow equation. Q is heat energy. Okay, so what we're usually calculating is heat energy. M is simply in the mass in grams. C is the specific heat that I just talked about. And every substance has a unique specific heat, so the number will vary. And delta T, change in temperature, and in science we always measure final minus initial, so that's how we're going to find that. Okay, so I have 4 variables here. I can solve for any of them as long as I have the other 3. Let's try this first example. So chromium, Cr, the specific heat is 0.4605 joules per gram degree Celsius. Okay, so that's this. That's C. If 215 gram sample, that's our mass, at 78 degrees, is placed in a cold environment and is reduced to 43.5 degrees, how many joules were removed from the sample? All right, so they were giving me two temperatures. It started at 78, so that's temperature initial. It ended at 43.5, so that's temperature final. And the question is, how many joules? Okay, so it'd be a good idea to grab your calculator so you can go along with these equations so that you're used to using the equation. Start by writing the equation and then rearranging the variable you're trying to find. So Q is equal to MC delta T. And I am solving for Q, so it's arranged the right way already. Let's go ahead and substitute our values. 215 grams. Specific heat is 0.4605 joules per gram degree Celsius. And our delta T. So delta T is equal to TF 43.5 minus T initial 78. So that's a negative 34.5. And that's degrees. Okay. Check our unit cancellations. Grams divided by grams. Celsius divided by Celsius. The only value that's left is joules, which is what the unit of heat should be. So 215 times 0.4605 times negative 34.5. Okay, so negative 3415.758. We will have to round this. We can keep 3 sig figs, so it's gonna be about negative 3420. And it's okay that the number's negative because the negative sign means that it's losing heat. Anything losing heat will have a negative value. Does that calculation make sense, guys? Okay. All right. Why don't you guys try the second one on your own? Trying to find the final temperature, TF. So let's start with a prediction first. This water is absorbing energy. What do we expect to happen to the temperature? Should increase, right? Should go up. Okay. So there's a couple ways to do this. I think the simplest way is to just rearrange this for delta T first. So that's what I did here. Q over MC is what is going to be equal to delta T. We do have all these values, so we can plug them in. So if I take 652 joules divided by the mass of 15 grams, and the specific heat is 4.18 joules per gram degree Celsius, this will give me degrees Celsius. Let's double check our unit calculation here. Joules over joules, grams cancel grams, so we're only left with Celsius. Okay, so when we calculate this, I get 10.4. So if we expect the temperature change to be 10.4, but the problem is telling you the water is absorbing energy, then you know the water must be increasing in temperature. So therefore, temperature initial 20 plus 10.4, 30.4 degrees is equal to T final. Or you could have substituted this for T final minus T initial and plugged everything in that way, and you would have gotten the same result. Okay, so either way works. But, you know, try to read the context of the problem. So make sure you understand, you know, what should happen. Should it go up? Should it go down in temperature? Because what's happening with the energy? Is the energy coming or is it going? In this case, it's being absorbed, so the temperature should go up. Okay. So example 3 is another problem just like this. Tungsten is an element, it's element W. And it has the highest melting point of metals. So it's really, 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 really hard to melt. So we use it in light bulbs. In a light bulb, there's a filament, a wire of tungsten, and when you screw in the light bulb, the electricity travels through the wire and it emits a really, really bright light. Hence, it's used for light. Okay, and we know that it won't melt, so it's okay to send lots and lots of electricity through it, and it just makes the light really bright. So, anyway, we're trying to find the specific heat of tungsten. So, we're going to set up the equation the same way, or similarly, but this time we're solving for C. So, divide out everything except for C, and you get Q over M delta T. The energy is given, except that the units are not right, because specific heat has to have certain units. Specific heat has to be joules per gram degree Celsius. So we've got to change from kilojoules to joules. All right, so in other words, 256 joules. So 256 joules divided by 0.75 grams, and our temperature increases by 2550, so that is our temperature change, 2550 degrees Celsius. And, oh, actually the answer was already there, 0.134. Okay, are we getting more comfortable with the heat flow equation? You got 4 variables, 5 if you count your temperature initial and temperature final as separate. Okay, so if we know that heat goes from the hotter object to the colder object, and we know there's this concept called specific heat, substances have different specific heats that dictates how much energy is needed to raise the temperature or lower the temperature. We can actually use this information to help us solve the amount of heat that takes place in chemical reactions, or even solve for other specific heats. So I'm going to add another page here and just kind of give you an example, a preview of the lab that we'll be doing next day in class. Okay, so here's how it's going to look. There will be a hot water bath, and in that hot water bath will be a thermometer. Right, we'll have this water boiling, so the temperature will basically be around 100 degrees Celsius. Maybe a little bit lower, but around there. And there's going to be a piece of metal. Now, let's say for argument's sake that the metal weighs 50 grams. So let me ask you a question. This water here has been boiling now for an hour. This metal has been sitting in that boiling water the whole time. What temperature is the metal? The number is actually written on the screen. What's the temperature of the metal? 100. The metal got to the same temperature as the water. They are both the same temperature because the metal's been sitting in that hot water for so long. Okay? So, temperature initial for the metal equals 100 degrees. Okay. At my lab bench, I've got a styrofoam cup that's got water in it. Let's say that there's 100 grams of water. The temperature of this water is, let's see, the problem tells me 25 grams, 24 degrees. Okay. Now the specific heat of water is constant. It's known. It's 4.18. This is the value. We don't expect you to memorize this. We'll give this to you on the test, right? You probably will memorize it because we'll be doing these problems so often. So for the water in this cup, it's 100 grams. Temperature is given. Specific heat is given. Okay. So what's going to happen is this. I'm going to take this metal from the hot water bath and place it into the cup of water. When I do that, the temperature reaches a maximum of 28 degrees. So T final is equal to 28 degrees. If that's the final temperature of the water in the cup, what is the final temperature of the metal? What happens when something sits in the same place for a really long time? It's going to be the same. It's going to be the same. So T final is for the water and metal. The final temperature is the same for both of those. So what has happened here? I took a piece of metal that was hot. I placed it into a cup of cold water, and the water temperature went from 24 to 28. Does that make sense? Something hot warmed up a sample of water, right? Okay. So the heat transferred from the water, Q from the metal, is equal to the heat of the water, except that it's opposite. Because the metal cooled down. I took the metal, a hot piece of metal, and cooled it down, so that's why the negative sign is in front of the metal. But it's the same number. So, if that makes sense, Q is MC delta T. Except that the left side is for the metal and the right side is for the water. Do we know the mass of the metal? Yeah, right, it's right here. Do we know two temperatures for the metal? We know the initial was 100, the final was 28. So yeah, so this is here and here. The goal of this problem is to find the specific heat of the metal. That's the goal. Let's go over to the water side. Do we know the mass of the water? Yeah. It's right here. Do we know the specific heat of the water? Right here. Do I have the final and initial temperature for the water? Yeah. Here and here. Okay. The goal is to try to find the specific heat of the metal, and I have all of the variables that I need. So let's go ahead and calculate what this is going to be, and we'll substitute our values. So we'll do the water side first. So the mass of the water is 100 grams. The specific heat of the water is 4.18 joules per gram degree Celsius. T final minus T initial, 28 minus 24, that's 4 degrees. Okay. Now, if the goal is to find C of metal, I am going to divide by the mass of the metal and the temperature change of the metal. So the mass of the metal was 50 grams, and the temperature change of the metal, T final minus T initial, 28 minus 100, or negative 72. Note that the negative signs cancel each other. So let's find out what our value is. .464 joules per gram degree Celsius. Okay, so this is a preview of Wednesday's lab. This is exactly what you're going to do. You're going to take a metal, you're going to transfer it to a cup of water, you'll take measurements, you'll take all the temperature measurements, you'll take all the mass measurements, right? And once you have all the data, then you can go ahead and calculate for the missing value, which is C. Okay.